Okay, so this tutorial I have 3 additional questions on AM. It's mostly just going to be drawing stuff. So it's going to be a relief from what we did last week, or last Wednesday. Okay, so it's a little long here, but I'm going to go through it slowly. Okay, so we've got 2 different signals. They're both band limited by 4,000 radians per second, and they're going to be transmitted together simultaneously. So you can think of this as kind of like a miniature frequency division multiplexing. That's all right. So we have the first spectrum here. So this is M, the first one, M1 of T, and then this is the second one. So basically what we got to do is you got to put it through this entire, this block diagram, or this whole process, and we have to figure out what the Fourier transforms of the spectra are at each point in this diagram. Okay? So also note that we have a, let me see here. At point D, we have a bandpass filter that is represented by this equation. So this is a bandpass filter. So the center is at 40,000 radians per second, and then there's some channel bandwidth or some bandpass filter bandwidth W that we have to figure out. Okay. We also know that at this point, so you're going to, these two are modulated. You add them up, and then you modulate it again by some frequency omega c, and then this is bigger than 10,000 radians per second. So that is something that is given to us as well. Okay. So the first point is to sketch the spectra at all the points. Okay, well, I'm going to call this MAF. Okay, this is given in omega, so I'm going to sketch it in omega. So at each of these points, I'm going to call them, M sub C and M sub D. Okay, so that's how I'm going to identify all these. So let's figure out what the spectra is at M sub A first. So let's actually calculate what it is, and then we can see what it is after. So MA of T, okay, is simply what? It's just your message, the first message, and then it's multiplied by 2 cos, and then it's at 10,000. Okay? If I want to find the Fourier transform, okay, remember what it was. If you just said M1 of cos, it was a half, but then because we have a factor of 2, that constant goes away. So you could think of this as 2, and then we had a half M of omega minus 10,000, right, and then M of plus, right? Okay, this here is because of M of 1T, and then cos of 10,000. Okay, and then this is a 1 here, sorry. Okay, and because there's a factor of 2, that goes into there, right? So the factor's on the outside, and then when you carry this over, right, these halves go away, so we're left with just the signals that are just shifted themselves by 10,000 radians. So let me go full screen here. Okay. Okay, that's cool. Okay. So this means that I'm just going to take my spectrum of M1, which is this guy, and I'm just going to make 2 copies. Shift to the right by 10,000 and shift to the left by 10,000. So it's going to look like this. So this is 10,000. Minus 10,000. Also know that the height of the apex is equal to just some constant k. Okay? And remember, this is plus minus 4,000, so this becomes 6,000, and this becomes 14,000, right? Same thing over here. Okay, this is omega. Okay, so does everyone agree with me on that? I think it's pretty straightforward, yeah? Okay? Now, if you take a look at B, it's exactly the same thing. We're modulating by 2 cos, but the carrier frequency is different. And it's just, it'll be this one, but instead of doing plus minus 10,000, it'll be plus minus 18,000 instead. Okay? So I'll let you go ahead and do that on your own. So B, okay, you have M of B. Okay? I'll let you work that out on your own because it becomes M of 2, 18,000, plus M of 2. Okay, I won't do the work here. It's pretty self-explanatory. It's basically the same thing as A, but the carrier frequency has changed. It's not 10,000 anymore, it's 18,000. So this means that centered at 18,000 and minus 18,000, okay, we have 2 things that look like this. Also, the amplitude is K as well, okay? And at this point, remember, the bandwidth is 8,000, or it's plus minus 4,000, so this is 22,000, okay? And this is minus 22,000 and minus 14. So this would be M of B. Okay, and this is M of A, I guess. M of A. Okay. So are we in agreement with this one here? Yeah, it's just different signal, but the carrier frequency is different. So instead of doing 10,000, it's 18,000. So it's just different carrier frequency. The shape is different, but the concept is exactly the same. Okay, great. Now let's take a look at not B. Sorry, let me just do B. Okay, and this is at A. Okay, so now let's take a look at C. So C, all I'm doing is I'm adding them together, right? So this means that I'm taking this guy and then adding it with this one together. So notice that this one spans between 6,000 and 14K, and this one spans between 14K and 22,000. So if I were to add these two together, you're just going to get them right beside each other, right? So you have the hump that goes from 6 to 14, and then you have the kind of inverted kind of triangle that goes from 14 to 22, and you're just adding them up, right? So in this case, so it looks like this. So you have 1, 2, 3, 4. Okay. So here it's minus 22,000. This is 18,000. Actually, you know what? I'm going to do it in terms of K because I can't keep writing all the, numbers, the zeros, right? So this is 6, 10, 14, 18, 22. Okay. And then this is in terms of times 1,000 omega. All right. And this would be at the C, right? So remember, they're both separated so that when you add them together, that's pretty much what you get, okay? All right. Now D wants to take the signal that you see at C, which is added, and we're going to modulate by some carrier frequency, but we know that it's going to be bigger than 10,000. So basically what's going to happen now is you're just going to take this one here, and then you're going to go plus minus omega C. You're modulating again one more time, all right? So in this case, you're going to have okay, and then so here, and then here as well. Okay, also it's K as well because of that too. So if omega C is here, which we don't know yet, okay, this becomes omega C plus 6. Here is omega C plus 10, omega C plus 14, omega C plus 18, omega C plus 22, okay? And then here is omega C minus 6, 10, 14, 18, and this is 22. Actually, no, I'm sorry, it's the other way around. So here, 22, 18, 14, 10, and this is 6. Okay? And then we could do the same thing on this side too. So we have omega C minus 22 minus omega C 18, 14, 10, and then you get the picture. Right? This here is 18, and here is, oh, sorry. Yeah, this is fine, this is fine, this is fine. And then here, the axis here is omega times 10,000. Okay, so that's what it was. So what you're doing here is you're just taking C, the point of C, and then you're modulating by omega C. So this is where the center would be, and then you go in plus to the right, to the left, and that's what we get. Okay, yes? It'll still be K. The reason why is because if you take a look at what's being modulated, the amplitude is 2 again, right? So when you do 2 MFT, COSA, whatever, and when you're doing double side best press carrier, the 2 cancels out with each of the half factors, so it's still the same. If you were to get rid of these 2's, then what'll happen is that at A and B, you're going to get a factor of a half, so it becomes K over 2, and then at the output of D, it becomes K over 4. Right, because there's no factor 2 there. So the reason why the 2 is there is because you don't keep having the amplitudes at each point. Okay? So yeah, so with the factor of 2, it's still going to be K. If you got rid of this and then you left the 2's here, at A and B you still have the amplitude of K, but then after D, it becomes K over 2, right? Because that 2 is no longer there. But because the 2 is there now, it still stays as K. Okay? Make sense? All right. Fantastic. So there we go. There, that's not bad. Okay? Okay. Great. So let's take a look at the next question. Determine the minimum value of the channel bandwidth to accommodate the modulated signal consisting of two double sideband express carrier signals. Okay. So basically what they're saying here is that they want you to figure out the right bandwidth so that it spans the width of two of these signals. So you can choose any one you want. So the width between here and here is what? 22 minus 6, which is 16,000. Okay? So therefore, part B, the width is 16,000. So that is the bandwidth we need to accommodate both of those signals together. Okay, so width is the width we need. Okay, that's very simple. So you just have to choose. So what we need to do is the output of the band. So if you take a look at this diagram, what we need to do is we have to design the appropriate channel so that it only contains two signals. So if you take a look at part D, we actually have 4 copies of the signal. So 1, 2, 3, 4, right? I want to design a filter so that I only retain 2 of the signals instead of the 4. Okay? So all I need to do is design a bandpass filter so that I can get any of these 2, right? So as long as I filter, so if you take the difference between either one of these, you'll still get 16,000. It's 22 minus 6, right? So 22K minus 6K is 16,000. So that's basically the width that you need. Very simple. Okay. The next question, using the value of W specified in part B, determine an appropriate value for the carrier frequency so that at point D you can transmit it over. Okay, so what this is saying here is that this bandpass filter is centered at 40,000. Okay, that's very important. So that means that you have to have a bandpass filter here where the center is 40,000. Okay? So for the center to be 40,000, I have to figure out what the limits are to make sure that I get it to be 40,000. So remember that the bandwidth is 16,000. Okay, so the pass band is between 32,000 and 48,000, right? Because you want to have your bandpass filter such that the center is at 40, but then it's between 32 and 48 because the width is 16,000. Okay? So you have to figure out the right carrier frequency. You have to figure out what this omega C has to be so that you get your bandpass filter to go look like this. And that's actually very simple. Okay? There's 3 ways you can do it. You can make it such that omega C plus 6,000. So at this particular point, you have to make sure that it's equal to 32. So at the very end of this is omega C plus 6K, right? And this is omega C plus 22. At either of these ends, you have to make sure that once you add the carrier on top, you will get this to match. So this is one way to do it. Another way to do it is to simply do omega C plus 22,000 is equal to 48. And when you solve for either one of these, you'll get omega C to be 26,000. Okay? So you have to make omega C 26,000 so that you will shift your signals to 40,000. That's where the center of the bandpass filter will be. And then you have to make the width of the rect function of the bandpass 16,000 to filter out those signals. So it's gonna, you have one that looks like this, right? And then you have one that looks like that. So the answer is 26,000. Okay? Yes? Is 40, yeah. Yeah, you can also do omega C plus 14,000 is equal to 40,000. Same thing, and you also get 26, right? Because at the center here, this guy, you want to make this equal to 40,000. Same thing, doesn't matter, right? Because you're shifting all the frequencies by the same amount. So you can either do the end, do the middle, the beginning, it doesn't matter. But either one of these 3 will give you the same answer, which is 26. Okay, so was that your question, I think? Okay, fantastic. Okay, any questions so far? Okay, so last question here. Design a receiver to recover the signals M of 1 and M of 2. All right, so the process to do this is actually quite simple. So if you take a look at the sketch that I did previously, we can see that both of the signals, at least this is on the positive side, we can see that both of these signals occupy between 32,000 to 48,000. Because if omega C is 26,000 radians per second, this means that the lower end has to be 32,000. We've already established this. And the upper end is 48,000. So right in the middle is 36,000 for the first signal, which is, sorry, it's the second signal, which is M2. And the first signal spans between 40 and 48. So all we need to do is you have to specify, so this signal's coming in, we need to specify the frequency for the modulator, for the cosine wave, such that one of them is centered at 36 and the other one's centered at 44. So that when you modulate this signal, both of their portions get translated down to the baseband, which is between minus 4,000 and 4,000. Okay, so basically, so the first signal, let's do D, is concentrated, sorry, not M, so M1 of W is concentrated between 32,000 to 40,000 radians per second. And the center is at 36,000. So we'll choose to be omega 1. And then the second signal is concentrated. Actually, I'm sorry. This is the second signal. It's first. Sorry. So this is. Let me just double check one more time. Yeah, the first one is the hump. So, sorry. This would be the second signal, and then the first signal. Concept's still the same though. It's concentrated between 40,000 to 48,000 rads per second. Center is at 44,000. And then we'll choose to be omega 2. Actually, we'll make this omega 1 and this omega 2 to be consistent. Okay. So the reason why you choose the middle is because when you do the demodulation, you'll make it so that the center becomes at 0 at these frequencies, and then you get the baseband to be between minus and plus 4,000. So therefore, using the fact that we'll let the output be y of t, we'll call the output to be y of t. All right, so y of t is coming in, okay, and then we can split it into two different branches. Okay, so the first one, the message, or the modulated component will be multiplied by 44,000 rads per second, and the second one will get modulated by 36. Okay, and then you simply have to apply a low-pass filter to isolate out the frequency that you need, or the frequencies that you need, and then this output is just the first message, and this output is the second message. I also like to make sure to multiply the spectra by 2, so that you get rid of that half factor when you do the modulation scheme. And the pass band for the low-pass filter, okay, you're just going to go between minus 4,000 to 4,000 rads per second. Okay, so just a quick sketch. All right, so we see that the spectrum before was something like this, right? So this was actually, I'm just going to do the positive for now. Okay, so this is the spectrum. So we had one like this and one like that. Okay, so this is 44. Sorry, that's 44. This is 36. This is 44, and then this is times 10,000, and this is omega. Okay, so when you modulate by 44,000, okay, what's going to happen is that you're going to get two copies. So one comes from here, so we have one like this, and over here like that, right? So this is minus 4 to 4, and then you also have another copy when you shift over. So you have one copy here, and then you have one copy at plus 44,000. So you're going to have another copy over here. Okay, like that. And then this is at 44. Sorry, this is 40. So 40 plus 44 would be 84,000. And then once you apply the low-pass filter, right, you get this as the you get this here as the final output. And then you can do the same thing for this guy over here. I won't show you, but this is just one example where, you know, you want to choose the correct carrier frequency so that you get the right signal centered at, the baseband, and then you apply the appropriate low-pass filter so that you get the correct output. And then, you don't need this anymore. Okay, and that's it. Okay, so, all right, so message signal. Okay, so we have some message signal, and we have a couple of nonlinear devices. So the input is x of t, and then the output y is simply squaring it and applying some factor to it, alpha, which is greater than 0. Okay. Also, we have a carrier of 2 pi fc with some carrier frequency fc. Okay. So this is the diagram setup. So we have, this is our message. We have a spectrum here, and then we have this block diagram, and the output is actually a modulated signal. So here are the questions that are going to follow. Show that the output of this system is an amplitude modulated signal, plot the spectrum, and then explain how you use an envelope detector to recover the amplitude modulated signal. Okay, that's pretty easy. So what I'm going to do, okay, is I'm going to measure 2 different points. So not 2 different, I'm going to measure different points. I'm going to call this M of A, okay? I'm going to call this M of B, okay? Call this M of C, call this M of D, and then finally the phi is simply just, everything is subtracted together. Okay, so let's go through this one by one, all right? The first one is simply your message subtracted the carrier wave. Okay, so this is M of t, subtract cosine 2 pi fct. That's a no-brainer, right? You're just taking M and subtracting by whatever's coming in. Let's do the next one, just to be sure we're on the same path. M of t, and then plus, right? Okay, everyone's with me so far. It's just a subtraction at the top and addition at the bottom, right? Okay, so M of t subtract this carrier and M of t plus. So that is what's going on right now. Let's take a look at MC of t. MC of t basically takes the input into A and applies the squaring operation with an alpha. So you're doing alpha M of A all squared. Okay, so this becomes alpha M of t minus cosine 2 pi fct squared. And this becomes alpha of, so let me just, I'm going to square everything in and then multiply in, so this becomes M of squared t, okay? Subtract 2 M of t, and then there's an alpha here as well, cosine 2 pi fct, and then plus alpha cosine squared. Okay? This is just your standard expanding. So if you have a minus b squared, it's equal to a squared minus 2ab plus b squared. And that's pretty much what I did here. And then there's an alpha that factors in. So the alpha goes into here as well. All right? Now at part D, it's exactly the same thing. It's just you are applying it to b now. So you have alpha m of b squared. Okay? So I'm going to do the work for you. Instead of minus, it just becomes plus. So this becomes alpha m of squared of t plus alpha 2m of t cosine 2 pi fct, and then plus alpha cos squared 2 pi fct. Okay, right? So the only thing that changes is the plus, all right? And then the cosine squared stays the same. Now, let's take a look at E, which is adds. So what this does is that it'll take m of c, and so it takes m of d with cosine, and then it subtracts it with m of c. Okay, so this becomes m of e, sorry, this is phi. So minus m of c of t plus md of t plus cos 2 pi fct. Okay? Okay, so what you're going to do here is basically you're going to take m of c, so m of d subtract m of c. Okay, so what's going to happen here is that this guy subtracts with this guy, so this goes away, right? This and this add up together, so this becomes 4 alpha m of t cosine 2 pi fct, okay? And then also these guys and these guys cancel, and then you have an additional cosa here as well. So we get plus cosine 2 pi fct. Okay? So you're taking d and subtracting with c. So this alpha m squared goes away, these cosine squareds go away, and then you have this subtract that, which is adding it. So 2 and 2 become 4, and then you also have an additional cos here. I'm not done yet. So if I actually factor out a cos, I get what? 4 alpha m of t plus 1 cosine 2 pi fct. And this looks like a plus m of t, right? So this guy would be a, and m of t, we'll call it prime, I guess, is just 4 alpha m of t. So there you go. That looks like an amplitude modulated signal to me. Okay? In this case, your carrier is simply 1, and then your message is simply 4 alpha times the original message. Okay? That's it. You're just going through the block diagram, going from beginning to end, and then that's what you get. Okay, any questions here? Are we good? You sure? Okay. All right, plot the spectrum. Oh, that's going to be pretty easy. Okay, so remember what the amplitude modulated spectrum looks like. I'm going to do this in omega now. Okay, so remember you had the, so if I'm doing this, you're going to get a pi, and then you have 2 impulses centered at, okay, we're going to call this omega c. All right, so 2 pi f of c. There's 2 impulses. Okay, right, and then we also have 2 spectrums that are copied with a factor of a half. All right. So we get 1 over 2 m of okay? So that's what the spectrum looks like. Okay, so remember the original spectra looked like this. So there's a height of 1, okay? So with a height of 1, but then I also have a 4 alpha, and then I have to divide by 2. So this means that my height is actually 2 alpha in the end. So we're going to have omega c minus omega c. So we have 2 impulses centered here. And then a is simply, so this is just equal to 1, right, from before. And then, so this becomes pi, okay? And then we're going to have 2 other impulses that have a bandwidth, is it minus plus b? Yeah, w. So we're going to have one that looks like this. Okay, and then, okay, so this is minus omega c plus, minus omega c minus. Okay, and the height here is 2 alpha, okay? The reason why is because we have a height of 4, right? And then we have to divide by 2 because of this guy. So because of this, that's why you get a height of 2 alpha instead. All right, pretty sure. Yes. Yep, 2 alpha. Okay, so any questions here? This is omega, of course. Right, okay. The next one is just hashing from the notes. So if you want to have an envelope detector, so you have your amplitude modulated signal coming in, you have to put it through an envelope detector, right? Oops. So, okay. So this stage here, no, this stage here would be an envelope detector. They're asking you to design a non-coherent demodulator, okay? Then you put it through a low-pass filter, and then you put it through a DC block. Okay, so here is a DC block. Okay, so we have a diode, and then we have some capacitance, some resistance, and then we'll call this C2 and R2. It doesn't have to be the same. So you have an envelope detector. This is a low-pass filter. And then you have a DC block. So that's basically how you do it. So you have an envelope detector first that will detect the envelope, low-pass filter to get rid of the ripples, and then you have a DC block to change the offset so you get the original message signal back. That's really it. Okay, explain how you can use a non-coherent. Please provide a block. Yeah, so this, yeah, so that's pretty much all you do. Okay, that's the question. Right, so those 3 components make your non-coherent detector. So you have an envelope detector, low-pass filter, and then DC block, and that's it. Okay, yes? Or yeah, you know what? It's up to you. If you don't remember it, then just you can just do it like this if you wish. Either one is acceptable. If you wish, you can either do it like this. You go envelope detector, and then low pass filter, and then DC block. You can do it like that too if you can't quite remember what it is. I'll accept both. If I ask you something like this, then this is good or that's good too. So either one, this or this. That's fine too. Okay, just remember those three in the sequence and you're good. So if you want, if you actually draw out the circuit, then that's great. But if you don't remember, just as long as you remember the three components and put them in the exact order, then that's fine. Okay? All right. No questions here? All right. Okay. This is the last one. Shouldn't take very long. Okay, this is actually, a lot of these are, this is actually a joke. It should only take me a few minutes. So we have a signal, some cosine wave with some fundamental frequency that's scaled by √2. And then this cosine is sampled by a periodic pulse train. Okay, that looks like this. So it's sampled by a periodic pulse train. So the width is tau seconds centered at the origin. So the width between here and here, this is tau. Okay. Also, it's repeated by TS second intervals. So this is the sampling time. Sampling time, sorry. Okay. So if we feed this spectrum, if we feed the signal into a spectrum analyzer, this is what it would possibly look like. Actually, you don't really need the spectrum. It's just putting it here just for completeness. So this is what would happen if you were to take the sample signal using a pulse train, and then this is what the spectrum analyzer would look like. So A, determine the Fourier series coefficients for the pulse train. Okay, that's totally fine. So A, Fourier series coefficients. If you remember, you have the period, and then if you know what the Fourier transform is for one of the values, you just substitute n omega naught, and then you're done. Okay, so instead of doing the traditional method, you can do it this way. So x of w is simply a pulse, just a single pulse. Sorry, if this is with t, then this would be tau over 2, and this is minus tau over 2. This is just simply a rect function, right? Okay, so if I took the Fourier transform of a rect function, this becomes tau sinc omega tau over 2. All right? So this is what I know of the Fourier transform to be. So all I have to do is take this and substitute n omega naught in, and then I'm done. Okay, so d of n equals 1 over ts tau sinc omega tau over 2, where omega is n omega naught. In this case, not omega naught, it's omega s. Okay, where omega s is just 2 pi over ts, right? N and then 2 pi over ts. Okay, so 2 pi over ts. Okay, so we got tau over t of s sinc, and then we have n 2 pi divided by ts tau over 2. Okay, so the 2's will go away, okay, and then the pi stays the same. So what's going to happen is this becomes tau over ts sinc n pi tau over ts. And that's it. Okay? That's it. So you remember this property is very important. Okay? So if you want to find the Fourier series coefficients for a periodic version of the signal, just find the Fourier transform for one instance and then substitute n omega naught or omega s or whatever instead of omega and divide by t of s and you're done. And that's it. Okay? That's the first question. Very simple. Next question. So we are given that this is the Fourier. So we are given that when you take a look at the spectrum analyzer, what we see is this. So this is the Fourier transform of the. So this is the Fourier transform of xs of t. So this is what is given. So when you take a look at the sample, this is what we get. We have to figure out what the fundamental frequency is, sampling frequency, and the width of the pulse. Okay. So the fact that your signal is a cosine is very important. This means that when you are sampling, you see copies of the impulse at every multiple of your sampling time or your sampling frequency. Okay? So this here is one cosine, right? This is another cosine and so on and so forth. Okay? So if you take a look, remember that this is symmetric, right? So in between here is 18, in between here is 36, in between here is 54. So I would say that the sampling frequency is going to be 18,000. Okay, 18 kilohertz, right? So also this is, so they're taking this and they're multiplying by 2 pi. So this actually would be in hertz. This is actually hertz, okay? So the sampling frequency, if you'll agree with me, you see copies of multiples of 18. So I would say that the sampling frequency is 18 kilohertz, okay? Also, take a look of the width between the sampling frequency. You see this is 20, so this is 2 and minus 2. So remember, when you take the cosine, you have impulses that are plus minus a certain frequency. So because the difference between the carrier is 2, then the fundamental frequency, I would say, is 2 kilohertz. Okay? So B, the fundamental frequency is 2 kilohertz. Okay? The sampling frequency is 18 kilohertz. Okay. Now we just have to figure out what the width is. And that's actually very simple to do. Okay? So let's see here. Actually, it's already given to us. So you see here, sinc omega 10 over 5, 10 to the 5th. So we had sinc, so we had tau, sinc omega tau over 2, okay, equals some, 1, and then sinc, 0.36, sinc omega, let me see, omega over 10 to the 5, okay? We can't just set tau equal to that because that, you have to use this and set this equal to this here, okay? Because there's probably some unknown factors that you have to consider. So this becomes omega tau over 2 equals omega 10 to the 5. So the omegas cancel. So this becomes tau equals 2 divided by 10 to the 5, which is equal to 2 times 10 to the minus 5. So that's what you do instead, okay? So this 0.36, remember, you can't just use this blindly because the spectrum is RMS. So there's a factor that is on top of the magnitude. So you cannot just use this. So this doesn't work because of RMS. Okay? So you'd have to use the internals instead. So you set this equal to that because that's what is given to us, and then we see that the pulse is equal to 2 times 10 to the minus 5. Okay? Comment on whether x of t can be recovered from sampling. If your answer is no, state your reasoning. If the answer is yes, how can you recover it? Okay, sure, no problem. Well, you can see here that the sampling frequency is much, much larger than the fundamental frequency. So all you have to do is just put a low-pass filter centered at around 2 so you get the original signal back, right? Because if the only way that this would not be recovered is if your sampling frequency was much less than the 2. So the minimum frequency you need to sample will be 4 kilohertz. You have to go twice the fundamental frequency. In that case, then you would have to design a low-pass filter exactly between 0 and 2. But because the sampling frequency is much larger, all you got to do is just put a low-pass filter right here, right? And this is minus 2 over here. And then you put a low-pass filter, and then you just get the original spectrum back like that. Okay? So C, because f of s is larger than twice the fundamental frequency, this is the Nyquist frequency, no aliasing. Okay? Therefore, put a low-pass filter centered at 0, well, no, not centered, but with passband of minus 2 to 2 kilohertz. Okay? And that's it. Done. Okay, that's all I have for you today. Any questions here? Okay, so I'm going to start FM on Wednesday, and I'll do more amplitude. I'll do more AM questions for the tutorial on that day. So I will see you on Wednesday. Thank you.